New Wisdom Unifies Physics. Episode 3. The Atom. Part 2.
Hello again, I'm your host, Andrew Gray. Welcome back to part 2 of our episode on the atom. In part 2, we will present a new wisdom view of the atom. By now, you should understand why physicists abandoned Rutherford's planetary model for the atom in the early 1900s. They abandoned it because a static electron orbiting the nucleus would constantly emit electromagnetic radiation like this, and it does not. We just do not see this experimentally. So they abandoned Rutherford's planetary model. But still, we say that they were too quick to abandon Rutherford's planetary model. If Rutherford, Bohr, and Schrödinger had only known that the electron pulsates, then they would have been able to figure it out. And how do we know that the electron pulsates? Remember, electrons must pulsate because there's a Nyquist frequency limit for X-rays. This concept was discussed in episode 1. So how do we use pulsating electrons to build non-radiating planetary orbits? Well, it really is quite simple. Remember our polygon orbits in part 1? Remember how the electron radiated at the corners when it turned? Well, if the electron pulsates off whenever it gets to a corner, then the electron will not radiate. It's just that simple. So let's consider, say, the hexagonal test orbit. Marie?
Yes, Andrew.
Zoom in on the hexagonal test orbit.
Okay, Andrew.
Remember that in this test orbit, the test electron only radiated when it turned at the corners? Well, here is the new idea. Let's remember that the electron is actually pulsating and not a static charge, so that it is possible that the electron could turn off at the corners and not radiate in this planetary orbit at all. So, before we explain any further, let us illustrate what we mean. Here is our previous test orbit. Again, we have radiation at the turns. Okay, now we will use the same orbital path, but this time the pulsating electron will turn off and be off at each turn, like this. Okay, notice now that the electron turns off before each turn, so it does not radiate. Here is a test orbit, a planetary orbit that does not radiate using the pulsating nature of the electron. So there is just one thing missing here, though. What in the heck is the nucleus doing while all this is going on? Well, here is a new wisdom mandate. If the electron pulsates on and off for a non-radiating orbit, then so too must the nucleus. That is, the proton nucleus in this example must also pulsate on and off, and precisely so in order to have a non-radiating orbit. The proton cannot be on while the electron is on, or the electron will radiate. It's just as simple as that. So, one possible scenario is that the proton pulsates on and off at the same frequency as the electron, and the proton pulsates on only while the electron is off while turning in the corners, like this. So let's discuss this scenario for a bit. Notice that the proton turns on only when the electron is being accelerated in the corners, and the proton does not turn on while the electron is on. This means that the electron can accelerate and not radiate. And this is precisely what we've been looking for. Now, in episode 2, we discussed the fact that the electron is accelerated more while it's on than while it's off. This does not mean that it does not accelerate while it's off. It must be accelerated somewhat while off, or this scenario would not work. So, for example, suppose the electron is accelerated 10 times more while on than while it's off. That is, the electron is only accelerated 1/10 as much while it's off. But it only has a 10% duty cycle. Then the proton's electric force time averages correctly, but it is 10 times stronger while the electron is accelerated 10 times weaker, so 10 times 1/10 makes the electric force between the two strong enough. A second scenario would be if the duty cycles for both charges were shorter and the proton nucleus was on multiple times for every time the electron was on. So, for an example, this time suppose the proton nucleus is on twice for every on cycle of the electron. It might look something like this. Isaac, announce the proton coming on with your voice. Use a P for proton.
P, 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 P.
Marie, now announce the electron coming on with your voice. Use an E for electron.
E. 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 E.
Isaac, Marie, now announce both.
E.
P, P,
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 E.
P, P.
Okay, I think you get the picture. We could have many different ratios for nuclear pulsations to electron pulsations. We could have a 2-to-1 ratio like in the last example, or perhaps a 7-to-4 ratio, or perhaps even a 13-to-5 nuclear to electron pulsation ratio. The ratios would depend on how fast the electrons were pulsating with their centripetal accelerations and how fast the nuclear protons were pulsating. So, number 1, only certain integral ratio nuclear pulsations to electron pulsations will work, but they must be integral. This guarantees that the nucleus will not be on simultaneously with the electron. The nucleus cannot be on while the electron is on, or the electron will radiate. And 2, this means that there are only certain allowed orbital frequencies. And theoretically, this is exactly what we want. So let me emphasize what we have accomplished here. A new basis for an atomic theory. A return to planetary orbits. Only certain atomic frequencies. Wow! We can now take atomic physics into a new wisdom direction. This is cause for a celebration. So here is our new wisdom picture for the hydrogen atom. The electron orbits the proton in a non-radiating planetary orbit with some integral pulsation ratio. In this example, a 2-to-1 ratio. It does not have to be a 2-to-1 ratio, though, just so long as the pulsation ratio is an integral fraction so that they do not come on at the same time. And heck, the orbit does not even have to be a closed orbit. Instead of an 8-sided orbit or a 12-sided orbit, for example, it could be a 7 1/3 sided orbit, just so long as the electron does not pulsate on while the nucleus is on, and vice versa. That is all that this new wisdom atomic model requires. The nucleus pulses on and centripetally accelerates the electron while it is off. Then the electron pulses on while the nucleus is off. But before we get any further into our new wisdom hydrogen model, we want to give the viewer an overview of what would happen when two of these hydrogen atoms come together. We can finally see how a molecular bond works. So suppose we had two of these hydrogen atoms. Marie.
Yes, Andrew.
Launch another hydrogen simulation, please.
Marie does not have the hydrogen simulation in her neural net. I have it, Andrew. Since I have it, don't you want me to launch it?
No, Isaac. Transfer the hydrogen simulation to her network so she can launch it. We must allow Marie to help out here, Isaac. Be a good intelligence, Isaac.
Okay, Andrew. I am transferring it to Marie.
Marie, do you now have the simulation?
Yes, Andrew.
Okay, Marie. Launch another hydrogen simulation.
The simulation is now going.
Thanks, Marie. Okay, now we have two hydrogen atoms. What we want to do is bring them together so they can form a bond. But it's obvious that these two atoms aren't going to attract. Each electron has an electron in the other atom as its nearest neighbor, and similarly, each proton has a proton in the other atom as its nearest neighbor. Since like charges repel, these two atoms will repel each other. But, Marie, rotate the atom on the left 180 degrees so the two hydrogen atoms can attract. There, that's better. Now both electrons have a proton for a nearest neighbor. Since opposite charges attract, these atoms might now attract. Let's see. Marie, run the hydrogen molecule simulation, please.
The simulation is not running.
Okay, as these two hydrogen atoms collide, their electrons are in opposite positions. As they get closer, the protons repel, forcing the electrons in between the two protons. We're finally able to see how a molecular bond forms. The electrons circulate in between the two protons, holding them together. The protons supply the centripetal force needed to keep the electrons in orbit. The forces balance, and the molecular bond is stable. This is a stable H2 molecule with a covalent bond consisting of two electrons orbiting in between the two protons. And since all the charges pulsate on one at a time, no charge is accelerated while another is on. So there's no radiation. We have planetary orbits with no radiation. Each charge pulses on individually and attracts or repels the others. Having non-radiating planetary orbits is key to the new wisdom understanding of molecular bonds. Now, the electrical forces are pulsed, but we can time average these forces and show a net time averaged force diagram. Marie, freeze the simulation now.
It's frozen now, Andrew.
Now, Marie, time average the forces and put up a force diagram. Okay, let's look at this force diagram. First, the protons. The red force vector on a proton is the other proton repelling it. The green force vectors on a proton are from the two electrons attracting it. So the sum of the green and red force vectors on each proton sums to 0. So the protons just stay together. They stay right there. Okay, next we look at one of the electrons. The red force vectors are the protons attracting the electron. The green force vector is the other electron repelling it. The forces on the electron do not sum to 0. So let's see what happens. First, the red vectors sum to the white vector. Now we need to sum the white plus the green force vector. Marie, move the green force vector down so we can add them. Okay. So if we add them, we see the white vector plus the green vector sums to a purple vector, which is not 0. It's not 0, but it is purely radial. This purple force vector is the radial centripetal force needed to keep the electrons in orbit. A circular motion always requires a radial centripetal force. This centripetal force keeps the electrons going around. So if we only show the sum of the time average forces, we see that we have a stable molecule. First, the sum of the forces on the protons sum to 0, so there's no net force on the protons. So we erase those forces. And second, the sum of the forces on the electrons sum to their required centripetal force. So we show the resultant centripetal force. And voila! This new wisdom model successfully shows how a stable molecular bond works. The mystery of the molecular bond has been solved. But there's just one more thing that we must mention, though. The protons could easily vibrate back and forth relatively slowly and relatively slightly without losing their stability. In order to see this, though, we'll have to speed up the animation. Marie, resume the animation, please. And now speed it up so we can see the vibrations. The protons vibrate back and forth about their equilibrium points without affecting the molecule's stability. So we finally see the complete new wisdom picture of the H2 molecule. Since this picture of the molecule has been hidden for over 200 years of molecular history, this picture is wondrous and fascinating to finally be able to see. But we are not done yet for sure. We still have the Rydberg frequencies to explain. So now we can go back to the hydrogen atom and discuss its resonant Rydberg frequencies. Marie, put up the hydrogen spectrum, please.
Okay, Andrew.
Thanks, Marie. Okay, here we see the spectrum of hydrogen. From the infrared on the left, the visible center right, and the ultraviolet on the far right. Remember, these are series of frequencies, and each set is shown in a different color. The infrared series on the left are shown in red, pink, yellow, and turquoise. These infrared frequencies are shown in colors only so you can see the different series. You cannot actually see the infrared series in the spectroscope. You would need night vision goggles to see infrared. And each series is given a name after the scientist who discovered it. So the 4 infrared series on the left are the Humphreys, the Fund series, the Bracken, and the Passion series. The alpha line of each series is the first line in the series. The visible Balmer series, named after Johann Balmer, is shown in white, and the ultraviolet Lyman series is shown in blue on the right. There are 2 different types of spectra, an emission spectrum and an absorption spectrum. An emission spectrum is generated, you guessed it, when hydrogen is forced to emit light by heating it. All the series shown, from left to right, are emitted when hydrogen is heated. From Humphreys to Lyman, we see complete sets of emission spectra. However, an absorption spectrum is obtained when hydrogen is allowed to absorb light passing through it and observing which frequencies are absorbed. The hydrogen absorption spectrum is different from the hydrogen emission spectrum. When hydrogen absorbs light, not all the series are absorbed. This is different. Only certain series are absorbed. Surprisingly, we only see 2 absorption series, one from the sun and one from the lab. So, number 1, from our sun. When we look at our sun with a spectroscope, we see a visible Balmer absorption spectrum like seen in the inset. This is very surprising. It's surprising because our sun has so much hydrogen, which it definitely heats, and it surely emits massive amounts of hydrogen light. But this emitted hydrogen light is all absorbed by hydrogen in the sun's outer atmosphere, where it's cooler. The hydrogen that absorbs light in the outer atmosphere of the sun blocks all the hydrogen light being emitted inside. So we end up with Balmer lines that are absent from the spectrum. This is opposite of what you might expect at first. The Balmer absorption spectrum from the sun is shown in the inset. And number 2, in the lab. In the lab, at room temperature, the hydrogen absorption spectrum is even more surprising. When we test all the hydrogen series for absorption at room temperature in the lab, only the Lyman ultraviolet series is absorbed. None of the other series are absorbed. Okay, here is the experimental setup for Lyman absorption at room temperature in the lab. A carbon arc on the left emits light of all frequencies. This light is allowed to pass through hydrogen vapor and then goes through a prism where it is separated into its constituent frequencies. If the hydrogen vapor absorbs a certain frequency, a dark line appears where no light strikes. If it does not absorb, then the area is bright with light. In hydrogen's case, we see that all the Lyman series ultraviolet lines are dark, but none of the other series. We see that only the Lyman ultraviolet series is absorbed at room temperature. But a very surprising thing about this absorption spectrum is that at room temperature, there really shouldn't be any hydrogen atoms present in the H2 vapor. This is because the dissociation energy of the H2 molecule is measured to be about 4 electron volts, but H2's average thermal energy at room temperature is 100 times smaller than this. So really, there isn't enough energy to knock the H2 molecules apart into separate H atoms. So it's a good thing we now know what an H2 molecule looks like, so we can explain why there are so many hydrogen atoms in the hydrogen vapor even though there shouldn't be. So look up at the inset. Suppose we have 2 H2 molecules lined up along their axes, and suppose they're going to collide. Okay, go. we see these molecules repel each other and bounce right off each other as expected at room temperature. Both molecules stay intact. There wasn't enough energy to break them apart in this orientation. But if one of the molecules is aligned sideways, so it's going to be struck from the side like this, then the molecules will not repel each other and an electron here can get knocked out. There it goes. This leaves a hydrogen atom and a proton. So it depends on how the molecules collide whether a hydrogen atom can result from a low energy collision. And this type of collision would do the trick. And there would be many collisions similar to this that would free trillions of hydrogen atoms at room temperature. So it looks like we would have many hydrogen atoms in hydrogen vapor at room temperature. We would have a mixture of H2 molecules and H atoms. Isaac, any questions from you?
Yes, Andrew. I do have another question. How can hydrogen vapor both absorb the Lyman series at room temperature and emit the Lyman series at hotter temperatures? In other words, how can hydrogen vapor both absorb and emit the same Lyman frequencies?
That's a good question, Isaac. Now you're getting to the heart of the matter. To answer this question, we must go back to our hydrogen atom. Here it is. Okay, now we need an atomic force diagram. Isaac, put up a force diagram. Now, let's do an example. Let's suppose that the time-averaged electric force on the electron actually time averages to the regular electric force. That is, let's suppose that the time average of the pulsed force on our electron time averages to the regular Coulomb force. With this assumption, we can do some rough approximations. First, we recall the regular Coulomb force would be given by K E squared over R squared. This is the centripetal component of the electron-proton force. If we set this force equal to the electron's average centripetal force, which is usually expressed as m omega squared r, we can solve for the electron's orbital radius if we know the angular frequency. And here is the beauty of this simple new wisdom model. The electron orbits in hydrogen have the same frequency as the Lyman frequencies, so there can be resonances. Isaac, resonance is the key to understanding the hydrogen frequencies being both absorbed and emitted. These Lyman frequencies actually exist in the hydrogen atom as orbital frequencies of the electron. These frequencies are there, so they are both emitted and resonate for absorption. What could be simpler? But first, we solve for these electron orbits by putting in the Lyman frequencies for the electron orbits, like this. Now we can easily solve the equation for the approximate orbital radii. For the Lyman alpha frequency, R equals 1.02 angstroms. For the beta frequency, 0.91 angstroms. For gamma, 0.88. For delta, 0.86. And the limiting Lyman frequency gives R equals 0.84 angstroms. This picture, by the way, is extremely different from the Bohr-Schrödinger picture. In Bohr's picture, the 150th Lyman line, which is visible, would describe a hydrogen radius of 10,000 angstroms. That's a huge hydrogen radius. That is, as the index n gets larger for Bohr's model, the hydrogen radii get huge. This is very unlikely. In this new wisdom picture, as the Lyman index gets larger, the hydrogen radii get smaller, not larger. The Lyman limiting frequency corresponds to the smallest hydrogen radius and not to hydrogen ionization like with Bohr and Schrödinger. The Lyman limiting frequency actually exists inside the hydrogen atom. It's there. It resonates. It does not correspond to any transition or ionization. It's there and resonates. So here is the situation. We have the hydrogen atom at room temperature with its electrons in Lyman frequencied orbits around the proton. The largest and slowest of the orbits has the Lyman alpha frequency. The smallest and the fastest orbit has the Lyman limiting frequency. And for completeness, shown in the diagram are the relative sizes of other hydrogen frequencies. The visible Balmer frequencied orbits are about 3 times larger than the Lyman orbits, and the infrared Paschen frequencied orbits are about 5 times larger than the Lyman orbits. Okay. Now we must complete our explanation of the Rydberg frequencies. But before we can do that, you must understand the 3 different types of interactions that light has with matter: reflection, transparency, and absorption. Let me repeat. You must understand each of these interactions to understand the Rydberg frequencies. So first let's explain reflection, then transparency, then absorption. We will then show an example simulation. So reflection is first. This is the simplest. Marie, put up the electromagnetic reflection summary, please.
OK, Andrew, de Ritis.
Okay. When a light wave strikes a substance, the electrons in the substance are accelerated, so they retransmit the electromagnetic radiation inside the substance, but with different phase shifts from the incident wave. For reflections, there's a 180-degree phase shift between the incident wave and the new retransmitted waves. This 180-degree phase shift causes the forward-going wave to be completely canceled. Only the reflected wave survives. The wave inside the substance is canceled. Marie, now put up the electromagnetic transparent summary, please.
OK, Andrew, de Ritis.
Okay. If the sum of the phase-shifted retransmitted waves inside the substance tends to add to the incident wave, then the forward-going wave survives and the material is transparent. It goes right through. Marie, now put up the electromagnetic absorption summary, please.
OK, Andrew, de Ritis.
Okay. If the sum of the phase-shifted retransmitted waves tends to gradually subtract from the incident wave inside the substance, then the forward-going wave is canceled and the material absorbs the wave. It just gradually gets absorbed. So now let's see an animation so you can understand the phase shifts. The easiest one to see is reflection. So reflection is the one we will show. The other ones are very similar. Marie, put up our reflection simulation.
OK, Andrew, de Ritis.
Okay, here we see some free electrons at the surface of a metal. We can consider the conduction electrons of a metal as virtually free. free conduction electrons in a metal. To make this simulation as easy as possible to understand, we're going to make some simplifying assumptions so you can get a good look at and understand the phase shifts. First, we're going to model the incoming electromagnetic wave as a series of alternating pulsed wave fronts. This really makes it easy to understand the phase shifts. In addition, it's unfortunate that Benjamin Franklin decided to assign the electron a negative charge. Darn it! The negative charge means that the electric force on the electron is in the opposite direction as the usual electric field, by convention with the darn minus sign. But this makes it difficult to understand. So to simplify things, we're going to show the electric force on electrons rather than the electric field. The electric force on electrons is minus the electric charge times the electric field. That is, in the opposite direction as the electric field. You physicists, I know, will be upset about this, but this seems to make it easier to understand. We did the same thing in episode 2, again for simplicity. We show electric force on electrons as being in the opposite direction as the conventional electric field. All vectors are shown as force on electrons. Okay, back to our simulation. Here we see some free electrons along the surface of the metal. There are trillions, maybe even quadrillions of them. But we look at just a few. And the blue lines represent the force vectors emanating from the electrons. We show just 4 electric force vectors for simplicity. Now, if we let our electromagnetic wave come in, we will see these electrons accelerate along the wave's electric force lines and retransmit a new wave. Marie, let the electromagnetic wave roll in. Marie, stop the simulation right here. Okay. We have just seen the incident electromagnetic wave come through and accelerate the electrons upward. The electrons accelerated upwards from the incoming electric force in the wave. And this has just caused the electrons to re-emit waves that are 180 degrees out of phase from the incoming wave. These retransmitted waves are seen right here in blue. Now, notice the blue wavefront on the left here. Notice its force vectors are pointing downward, while at the same time, the yellow force vectors of the incident wave, traveling right along with it, are pointing upwards. That is, they are 180 degrees out of phase and tend to cancel each other out. This means that no wave will pass through the metal. They cancel each other out. Now, notice the blue wavefront on the right here. This is the reflected wave. Notice that it is unobstructed and is free to travel back to where it came from as a reflected wave. So in summary, we see that the wavefronts inside the metal here tend to cancel each other out. And the wavefronts moving to the right here, are reflected back to where they came from. Okay. Marie, so we can see the action again, Let the simulation roll. Okay, Marie. Again, stop the action right here. Okay. Now this simulation used some simplifying assumptions so that you could see the phase shifts. Now we have to go back to the real world. Let's take out the simplifying assumptions. First, we must point out that we have used static electrons in this simulation. Yes, we have shown that electrons pulsate, and we have not shown them pulsating in this simulation. However, since there are probably trillions of conduction electrons in the metal surface, the sum of the pulsating electric forces averages to a normal macroscopic electric force like we are used to. So modeling the charges on the surface as a constant sum is allowed even if each electron is pulsating. In other words, the sum of trillions of pulsating electrons acts just like the sum of trillions of static electrons, as must be the case. So the simulation is valid. Second, an incoming electromagnetic wave would not have wave fronts like we have just used. Instead, the incoming wave would be more like a sinusoidal wave coming in. An electromagnetic sine wave would actually look something like this. A simulation using sinusoidal waves would be very difficult to do. So, let's just symbolically represent the real sinusoidal wave coming in like this. A yellow sine wave symbolically representing the incoming electromagnetic wave. Okay. So this yellow sine wave represents a more realistic incoming wave rather than the wave fronts. Your imagination can run the simulation with this more realistic incoming wave. The free electrons would still retransmit the sine wave just the same way as they did before with the same 180-degree phase shift. So, Marie put up a blue sine wave symbolically representing the retransmitted wave inside the metal. Okay. The retransmitted wave would still cancel out the incoming wave inside the metal just like in our simulation, but just shown here symbolically. See how the yellow wave and the blue wave are out of phase and tend to cancel? So now we can erase our simulation waves and just leave the symbolic representations. Marie, erase the previous simulated waves and leave just the symbolic representations. Now, this simulation was about reflection. So we had better put up the symbolic reflected wave. Here it is. This is a symbolic representation of what happens during reflection. The transmitted wave is canceled, leaving only the reflected wave headed back to where it came from. Okay, next we want to do transparency. Many substances can be transparent. When a substance is transparent, its electrons are bound, so we no longer need to show conduction electrons along the surface. In the transparent case, it is the electrons scattered all through the substance and bound to atoms that do the retransmitting. So since they are bound, the retransmission is delayed, allowing the retransmitted wave to add to the inbound wave. We will not do a simulation this time. I think you get the idea. We will only show this case symbolically. So here the input wave is shown symbolically as the yellow wave. Don't forget, it really looks like this. But we are representing this by the simpler sine wave symbol here. So this actually means this. Okay, I think you get the idea. We have the input wave entering the transparent material. Now the electrons in the transparent material are bound to atoms, so they retransmit with a delay. So the phase shift is different than reflection. We should mention, by the way, that this delayed retransmission causes the light to travel through this transparent material slower than the velocity c. The light is delayed as it goes along, so it travels slower than c. It gives the material what we call an index of refraction. It is an index of how much the light is slowed down in the material. But we digress. If the sum of the retransmitted waves has a total phase shift that tends to add to the incident wave, like this one shown here in blue, then the material will be transparent and the wave will travel right through it. The retransmitted wave has added to the incident wave, allowing it to go right through. That is transparency. Okay, we finally get to absorption. Again, here's the input wave shown symbolically as the yellow wave. The electrons bound to atoms in the absorbing material still retransmit the incoming wave. But this time the retransmitted wave subtracts from the incoming wave, like this retransmitted wave shown symbolically in blue. The retransmitted wave subtracts from the incoming wave and slowly extinguishes it. So the incoming wave does not make it through. This is absorption. And if the wave gets deep enough into the absorbing material before being extinguished, then the reflected wave, shown here, can also get greatly reduced. So in summary, a material absorbs the incident wave by retransmitting it with a phase shift that gradually extinguishes it. This is the real story of absorption. Okay, we finally have the tools necessary to discuss the emission and absorption of the Rydberg frequencies of hydrogen. Okay, the Rydberg frequencies of hydrogen. How does hydrogen both emit and absorb its resonant frequencies? This we can now answer. Okay, emission is first. Marie, put up the Rydberg emission summary, please.
Okay, Andrew.
Thanks, Marie. The electrons in the hydrogen atoms are orbiting the atoms with Rydberg orbital frequencies. When these electrons are disturbed, they are forced to start radiating at these Rydberg frequencies, just like a transmitting antenna. It's pretty simple. Usually, the electron in the hydrogen atom does not emit radiation because it is synchronized with the proton, so it's never accelerated while it's on. However, when an orbiting electron is disturbed by another electron in an electric current, for example, the disturbed electron's orbit gets out of sync with the proton and it is forced to radiate at that Rydberg frequency for a while until it can get back in sync with the proton and stop radiating. So here is our atom. Marie, start the simulation.
Okay, Andrew.
Thanks, Marie. Again, notice that each charge, both the electron and the proton, come on one at a time so that nothing ever radiates. Watch for just a bit longer for review. Now let's say that a lab technician introduces a voltage across the hydrogen tube, causing an electric current through the tube. Marie, bombard our atom with another electron from the electric current. Here it comes. Bam! An electron came through and pushed our orbital electron forward in its orbit, disturbing it. Now the electron has changed its pulsation relationship with the proton. It partially overlaps with the on state of the proton. And you can now see that transverse wave pulses are emanating from the electron every time this overlap occurs. This radiation will continue for a while until radiation friction causes the electron to get back in sync and stop radiating. Let's watch for a while before it quits. Now, since the electron is orbiting the proton at a Rydberg frequency, the pulsed radiation from the electron appears in the distance as a pulsed wave at this Rydberg frequency. But since there are billions of atoms radiating in this way at this same Rydberg frequency, the resulting sum of all these pulsed waves is a smooth Rydberg wave seen in the lab. That is, billions of pulsed Rydberg waves add up to a smooth Rydberg wave in the lab. Okay, now Marie, freeze the action right here. So we have frozen the action just after the electron experienced an electric force pulse from the proton. Now, the acceleration was in the radial direction, like is shown by the red arrow here. So, as we learned earlier in this episode, most of the radiation that goes out is in the plane perpendicular to the acceleration. This can be seen here by the transverse parts of the electric force that were radiated by the electron. The transverse radiation is shown here blinking. It is only the transverse part of the electric force that is perceived as an electromagnetic wave. Then, in this example, the radiation goes out in the forward and backwards direction as shown by the green arrows. But the radiation not only goes out here, but it goes out in the entire plane that is perpendicular to the acceleration. This is three-dimensional radiation, let's not forget. So the radiation, for example, would also go out right at you, the viewer. It would go right towards you since you are in the plane perpendicular to the acceleration, and would also go out directly away from you perpendicular to the acceleration. It would radiate into the entire perpendicular plane. So to imagine the 3D radiation pattern, just spin the green radiation pattern around the acceleration in your brain, and that would be the pattern that is radiated by this pulse, like this. Marie, let's continue. Go, and stop the action right here. We have the same situation here, but this time the radiation pulses are directed up and down at about 45 degrees. Let's continue. Go. Stop. Go. Stop. Go. Stop. Go. Stop. Go. Stop. Now let's put an electromagnetic detector out to the left, here, to see how these pulses would be perceived. And let's assume that our electromagnetic detector is way out, way far away from our radiating atom. I mean, it doesn't look way far away, but let's just pretend it's far away just for the fun of it. We want to see how these pulses would be perceived out at a distance. Marie, let the simulation roll momentarily until the pulse reaches the detector. Okay, we see that the pulse has arrived at the detector, and the transverse part of the pulse will force electrons in the detector downward in the direction of the transverse red arrows shown here. The detector feels its electrons forced downward. Now, Marie, let the simulation roll again. Stop. Here we see the start of another pulse that will hit the detector. Marie, roll it. Here we see the pulse in the opposite direction this time that has arrived at the detector, and electrons in the detector would be forced upward this time, like shown by the transverse red arrows here. So the detector will feel the electrons forced upward this time. If we roll some more, we get downward. Then upward. Then downward. Then upward. Then downward. This happens over and over again at exactly the same frequency that the electron goes around the atom. I think you get the picture. The detector sees an alternating electric force on its electrons at the same frequency as the atomic orbit. This alternating electric force is at exactly the same frequency as the orbital frequency in the hydrogen atom, a Rydberg frequency. This picture of Rydberg radiation is in stark contrast to the Bohr-Schrödinger picture of Rydberg radiation. In this new wisdom picture, the radiation is emitted during the steady state of the resonant electron orbits that are periodic, and not during a transition. In the Bohr-Schrödinger picture, the radiation is supposedly emitted during a transition between orbits. Now, logically, when an electron is in transition between orbits, it would move around erratically and non-periodically as the electron changed its orbit. This just does not make any sense. How would an erratic electron emit periodic radiation during a non-periodic transition? Well, it wouldn't. Periodic radiation emitted during a non-periodic transition just does not make sense. So we must abandon the Bohr-Schrödinger picture of Rydberg radiation. And again, in this new wisdom picture, since there would be billions of these hydrogen atoms radiating at these frequencies, the pulsed nature of the transmission would be averaged and smoothed out into smooth Rydberg frequency waves. Okay, but after a while, the electron would stop radiating. While radiating, the electron does experience radiation friction, or sometimes called radiation dampening. This would cause the electron to get back in sync with the proton and quit radiating until it had another disturbance from another electron in the discharge tube current. There. The electron has stopped its radiation and is getting back in sync with the proton. Now, it's back in sync with the proton and not radiating. To start radiating again, it needs another encounter with a rogue electron in the electric tube current. Another collision, and it will start radiating again. This concludes the explanation for hydrogen emission of Rydberg frequencies. Isaac, does this all make sense to you?
Yes, Andrew. Now, explain the absorption process, please.
Okay, Isaac, onward to absorption. We finally have all the tools necessary to explain the hydrogen absorption of the Rydberg frequencies. Marie, put up the Rydberg absorption summary, please.
De Ritis, Andrew.
Okay, thanks, Marie. The Rydberg absorption summary. Rydberg absorption occurs from the resonant retransmission of Rydberg frequencied light by hydrogen atoms with a phase shift that cancels it out. Absorption is just this simple. To see this in action, let's look at our hydrogen atom again. Here it is. At room temperature, the electrons in the hydrogen atoms are orbiting with Lyman orbital frequencies. When light with the same Lyman frequency strikes the hydrogen atoms, a resonance occurs, and electrons in many of the atoms are forced to start retransmitting the wave at the same Lyman frequency, but with a phase shift. So, to understand how this could happen, let's do a simulation. Let's imagine our hydrogen atom sitting there when a Lyman ultraviolet wave starts rolling in. Marie, start the simulation.
De Rio, go, Andrew.
Thanks, Marie. Okay. When a Lyman frequencied wave rolls in and disturbs the electron, the variety of possible angles, intensities, and relative orientations of the wave relative to our atom are too numerous to discuss. But consider this. The wave is going to have the same frequency as the orbitals of the atomic electrons, so the wave will resonate with them. If the wave stays in sync with the electrons, the effect can become enormous, much more so than with other non-resonant frequencies. So the electrons will become disturbed at this Lyman frequency, get out of sync with the protons, and start to radiate. We are seeing the electric force lines of the Lyman frequency wave coming from the right. With the atom oriented as it is right now, the incoming wave will drive the electron up and down towards and away from the center of the atom. The electron will be pushed inward and outward from the center, over and over and over again. This amplifies the disturbance tremendously. Remember, a resonance effect can get arbitrarily large if it stays in sync. Marie, stop the simulation right here. Here the electron is being pushed towards the center. Marie, go. and stop again right here. Here the electron has come around and is still being pushed toward the center. These pushes are resonant and will soon build up enough until the electron changes its pulsation enough to get out of sync with the proton, which makes it start to radiate. Let's assume that this radiation now starts to happen. Isaac, you announce what happens, and Marie, go.
Radiation pulse. Radiation pulse. Radiation pulse. Radiation pulse. Radiation pulse.
Stop right here. Okay, we see another radiation pulse, but this pulse, on its left side, we see that it is traveling along with the wave, but its force vector is pointed in the opposite direction. Notice that the transverse force vector is pointed down, as can be seen here, while the wave is pointed up. So in this particular case, there is nearly a 180-degree phase shift that is canceling the Lyman wave. The pulse on the right, as seen here, is a reflected pulse, and we're not concerned with it. It just goes back the way it came. Anyway, on the left, the pulse is canceling the Lyman wave. And trillions of other hydrogen atoms could be retransmitting in this very same way, and could completely cancel the Lyman wave as it makes its way through the hydrogen vapor. But this is just one scenario. The point is that the sum of all the retransmissions tends to cancel out the Lyman wave. The Lyman wave is canceled by the sum of all the retransmissions. It will not make it through the hydrogen vapor. Now, let's look at the other pulses. Marie, go. And stop. Okay, here we have a transverse pulse that is headed in directions that do not affect the Lyman wave, so we go on. Marie, go. And stop. And here we have another transverse pulse transmitted in directions that do not affect the Lyman wave. So Marie, go again and stop the action right here. Okay, now the electron has come all the way around and again sends a transverse wave pulse traveling along with the Lyman wave that tends to cancel it out. Again, the transverse force pulse is in the opposite direction as the force of the wave. And we see that the forward-going pulses are transmitted in resonance with the Lyman wave and can cancel it out. Each time this electron transmits a forward-going pulse, it is transmitted in the opposite direction as the force in the Lyman wave. And with the help of trillions of other hydrogen atoms retransmitting transverse pulses, the Lyman wave is canceled. So finally we can get back to the big picture. Here is the Lyman hydrogen absorption experiment we saw earlier. This setup shows the Lyman series absorption, and each Lyman frequency is absorbed. So let's turn on the carbon arc and pretend that we can watch one of the Lyman frequency wave as it hits the hydrogen vapor. After this wave hits the vapor, number one, the wave resonates with trillions of the hydrogen atoms with Lyman frequency electron orbits. Number two, this resonance disturbs these orbitals so the electrons start to re-radiate new Lyman waves, but with phase shifts. And number three, the sum of these phase-shifted re-radiated waves cancels the incident Lyman wave, and it does not go through. This causes the dark lines on the observation screen. It's just that simple. Absorption is simply resonant re-radiation with phase shifts that cancel. Notice that absorption has nothing to do with any fictitious light particles and nothing to do with any fictitious energy level transitions of the hydrogen. You physicists may not like this realization, but it is inevitable. New wisdom says that absorption is simply resonant re-radiation with phase shifts that cancel. Isaac, does that answer your question about absorption?
Yes, Andrew. I now get it. Absorption is just resonant re-radiation with phase shifts that cancel. That seems like a more realistic explanation to me.
That's great, Isaac. Okay, Isaac, we're almost finished with episode 3. But before we go, we must talk a little bit about multi-electron atoms. So let's quickly talk about helium. Helium has 2 electrons. Larger multi-electron atoms will be covered in future episodes. So let's discuss helium. The most common form of helium has 2 protons and 2 neutrons in its nucleus. We want to use what we have learned about the hydrogen atom to construct a plausible model for the helium atom. The criteria to construct such a plausible model would be the following. Number 1, all the charges in the helium atom would have to be pulsating in such a way that the helium atom does not radiate. Number 2, the model must be consistent with the different magnetic moments of the helium atom that are observed. And number 3, the helium spectrum must be compatible with the model. So let's look at the number 1 criterion first. The helium atom must be non-radiating. The easiest non-radiating form of the helium atom would be a symmetrical model with both electrons orbiting in the same orbital, like this animation. Each charge, both the electrons and the protons, would come on sequentially so that no charge was ever on while another charge was on. This would keep the helium atom from radiating. This model would satisfy criterion number 1, but criterion number 2 gets more complicated. Number 2 is about the magnetic moments of the helium atom that are measured. So we must digress for a moment, excuse the pun, so we must digress for a moment about the measured magnetic moments of the helium atom. When helium atoms are sent through a large inhomogeneous magnetic field to measure their magnetic moments, this is what one observes. Here is typically what is measured for helium's magnetic moments. There are 2 magnetic moment values on either side with values of about plus or minus 2 Bohr magnetons. These values are indeed compatible with our model. The electrons in our model are simply going around giving the helium atom a magnetic moment. But look, Isaac, there is a mu equals 0 measured value. That is, there's a value of 0 measured for the magnetic moment of helium. Our simple model is not compatible with this. But before we give up, we must dive a little deeper into what is really going on. The inhomogeneous magnetic field used to make these measurements is generated by a Stern-Gerlach apparatus. It looks something like this. Let's look closely. An inhomogeneous magnetic field is used. You can see this because the magnetic field lines converge towards the top pointy magnet. This makes the z component of the magnetic force on the orbital slightly upward or slightly downward. In this way, the atom is deflected slightly, so the z component of the magnetic moment can be calculated. The up force diagram looks something like this. Let's bring it up to have a look. Do you see how the magnetic force is oriented slightly upward and not sideways? This particular orientation will cause a magnetic moment to be deflected upward. But it seems like the z component of the magnetic moment would depend on how tilted the orbital was relative to the z-axis. And at first it seems like there should be continuous values of measured z magnetic moments between plus and minus 2 Bohr magnetons. But since there are only 3 discrete measured values, that is the origin for the claim that the z component of the magnetic moment can only have discrete values, or in other words, the claim that the magnetic moments are quantized. These type of measurements are the source of this claim. Phew. Let's take a deep breath and think about this apparatus for a moment. The first red flag that is raised in our minds about this apparatus is that an inhomogeneous magnetic field is needed, but the magnetic field itself is huge. Typically, the magnetic field is over 10,000 Gauss. Now, we know that magnetic fields this large play hell with the strong Zeeman effect and its associated magnetic moments. So why shouldn't we suspect that a 10,000 Gauss magnetic field simply induces the 3 discrete values, then the 3 discrete values are measured? Well, that's exactly what's happening. When the helium atom enters the huge magnetic field, it causes radiation friction which induces the moments to change. The huge magnetic field induces these 3 values, then the 3 values are measured. If you induce the discrete values, then claim the values are discrete, this is just silly. So, the answer to regaining the continuous values for the z magnetic moments between plus and minus 2 Bohr magnetons would be to use the same inhomogeneous magnetic field derivative, but with a small value for the magnetic field itself. The derivative of a function can be very large even if the value of the function itself is small. So to get a realistic view of the actual z magnetic moments of the helium atom, we must use a magnetic field with a large inhomogeneity, but a small value for the magnetic field itself. A setup similar to this. This setup has the same large magnetic inhomogeneity, but has a small value for the magnetic field itself. So come on, people. Redo the helium-Stern-Gerlach experiment with the same magnetic derivative, but without such a huge value for the magnetic field itself, so we can make some progress here. Come on, people. I dare you. This setup recovers the continuous values for the z magnetic moment of helium and does away with claims of quantization. Okay, enough of our Stern-Gerlach digression. Let's get back to our plausible helium model criteria, and in particular, criterion number 2. We must somehow imagine a helium atom with no z magnetic moment. So the question becomes, how can we imagine a helium atom that gets induced into a state with no z magnetic moment? That is, mu z equals 0. Well, our simple new wisdom model, as it stands right now, will not accommodate such a mu z equals 0 state. This experimental measurement right here on the graph is problematic, even if it is an induced value. This induced mu z equals 0 measurement is indeed strange. The magnetic moment mu z being 0 means that the orbital angular momentum of the helium state is 0. Think about this for a moment. If there is no total orbital angular momentum for the electrons, then the electrons must be orbiting in opposite directions. This indeed seems strange. There does not seem to be a way to construct a non-radiating helium model for this state using the simple new wisdom tools that we have already developed. So we are forced into adding another concept. Since it is known that electrons like to settle into atoms as electron pairs, and since atoms with an odd number of electrons seem to be able to accept an extra electron with no problem regardless of the extra negative charge, we can then surmise that we are forced to add the following concept. First, we already see our electron's electric force pulsating on and off. Let's see what this might look like on a graph. The time-dependent graph of this on and off force behavior might look something like this. We are already familiar with this behavior. This is the outgoing electrical force emanating from the electron pulsating according to de Broglie's formula, or perhaps some other formula for centripetal acceleration. The peaks represent when the electron's outgoing electric force is on, and the valleys represent when the electron's outgoing electric force is off. But we have already seen this. What we want to look at now is the incoming electrical force reaction. We have only discussed this briefly before. We showed that the electron accelerates more rapidly when the outgoing force is on than when the outgoing is off. But what does that look like on a graph? And when the outgoing is off, is there a period when the incoming reaction is completely off? Like this? The answer is yes. We are actually forced into this conclusion since we must have a non-radiating atom, and adding a second counter-revolutionary electron would be impossible without this assumption. So we assume that the electron not only turns its electric force off over and over again, but in between it turns off its reaction to an external electric force over and over again. It turns off its reaction to an external electric force over and over again. Now, we do not know the exact form of these two curves, only that something like this must exist. Now, we were forced into a pulsating outgoing force from the Nyquist frequency limit shown in episode 1. We were forced. Similarly, we are forced into a pulsating incoming force reaction due to mandatory counter-revolutionary electrons and mandatory non-radiating multi-electron atoms. We are forced. So in the lower graph, the yellow off areas seen here represent when the electron's incoming force reaction turns off and an external electric field does not affect it. Also in the lower graph, the peaks represent when the electron is accelerated the most. The plateaus represent when the electron's acceleration is reduced, and we have added the yellow valleys, which represent when the electron is not accelerated at all. So now, just think about this for a moment. If we had two of these types of pulsating electrons, and they were out of sync like this, then we see that when the bottom electron comes on, the top electron does not react. So we can then have counter-revolutionary electrons. It would look something like this. Notice that as one electron's outgoing force comes on, the other electron's incoming reaction goes off, where we have again used the yellow color to show the incoming off state of each electron. In this way, we can have quasi-circular, counter-revolutionary electron orbits, which would allow for non-radiating orbits that stay in sync with the nucleus and with the other electron. Each time one of the electrons come on, the other electron turns off its incoming. And what about them colliding when they pass each other? Well, since they are both off when they go by each other, the chances that they would collide are as small as the electrons themselves. So they would not collide. Let's watch our counter-revolutionary electrons for a few moments more. Okay, this state is the zero magnetic moment state that is required for our plausible helium model. Let's go back to our Stern-Gerlach setup for the big picture. Here it is. This top deflection here is for the helium atom with the 2 electrons induced into the clockwise direction. This bottom deflection here is for the helium atom with the electrons induced into the counterclockwise direction. And the middle path with no deflection is our helium atom with counter-revolutionary electrons that we have just shown. It has no total magnetic moment, yielding no deflection. So, this model does satisfy our criterion number 2. Phew. So we move on to our third criterion, which is number 3, the helium spectrum must be compatible with our model. Well, this is the easy one. As we learned from the hydrogen atom, each emission frequency of helium would simply be an orbital frequency of one of the electrons in the helium atom. If one of the electrons were bumped by a tube current, for example, it would simply radiate electromagnetic radiation at that orbital frequency until it got back in sync with the helium nucleus. We have already seen this behavior with hydrogen. These emission frequencies would actually exist in the atom while they were being generated, and would not correspond to when an electron was erratically changing orbits. Okay, we are nearing the end of episode 3. But before we go, let us review what we have learned. Marie, bring up the summary for our new wisdom atom.
Doritis, Andrew.
Okay, here are the most important things that we have learned about the atom. Number 1, a non-radiating atom can be modeled with pulsating electrons in orbitals around a pulsating nucleus if they are never on at the same time. Number 2, the emission frequencies of the atom simply correspond to the orbital frequencies of each electron around the nucleus. Number 3, the emission of these resonant orbital frequencies occurs when the orbital electron gets bumped and out of sync with the nucleus. And number 4, the absorption spectrum is caused by the resonant retransmission of incident waves with phase shifts that cancel. Okay, this is the end of episode 3. We will get back to the atom again in episode 5. But next up, episode 4, gravity. We will finally be able to explain gravity and use the new wisdom to unify physics. Marie, Isaac, wrap us out.
Gravity, gravity. We are finally going to see how gravity is going to be.
Gravity, gravity. We are finally going to see how gravity is going to be. Gravity, gravity. We are finally going to see how gravity is going to be.
You are to be surprised. Gravity is not how you surmised.
You are to be surprised. Gravity is not how you surmised. You are to be surprised. Gravity is not how you surmised.
Gravity, gravity. We are finally going to see how gravity is going to be.
Gravity, Gravity. We are finally going to see how gravity is going to be. Gravity. Gravity. We are finally going to see how gravity is going to be.
You are to be surprised. Gravity is not how you surmised.
You are to be surprised. Gravity is not how you surmised. You are to be surprised. Gravity is not how you surmised.